Welcome to the deep dive. We're tackling something pretty foundational today. Software architecture. It's
Yeah.
that, invisible framework that can really make or break any software system. And look, it sounds intimidating, I get it.
It definitely can.
But our goal here is to sort of pull out the crucial ideas, the really important stuff, and make it crystal clear. Think of this as your cheat sheet to understanding how great software gets built.
Exactly. Because diving into new technical topics, it can sometimes feel like a bit of a slog, right?
Yeah.
But we're here to, light the way. We'll be focusing on the core puzzles that architects grapple with, the paths they explore to find answers, and the key takeaways that come out of that.
Right.
The aim is really to give you that essential understanding without getting totally bogged down in, super dense jargon.
That's the plan. We're going to be like detectives and storytellers, maybe. Wow. For each key area, we'll uncover the central problem, trace the steps towards a solution, and then really spotlight the most valuable insights. The material we're exploring, it covers quite a range, from the absolute basics like what even is architecture versus design, all the way through different ways you can actually structure these systems.
Okay, let's jump in.
So first, big question then. What exactly is software architecture? And crucially, how is it different from software design? It seems simple, maybe, but honestly, these terms get tossed around interchangeably all the time.
Oh, constantly.
And it can really muddy the waters.
Absolutely. The chapter we're starting with, it actually nails this distinction pretty well using a classic comparison. Think about building a house.
Okay.
The software architecture is like the blueprint, right? It shows the overall structure, the foundation, where the rooms are generally, how the plumbing and electrical systems are sort of laid out. The big picture.
And software design, in that analogy, that's about the specifics within those rooms, within those systems.
It's choosing the hardwood floors or the paint color for the walls, maybe the style of the kitchen sink. Important stuff, yeah, but it happens within the framework the architecture already set up.
Got it. So architecture provides the high-level rules, the constraints, the kind of vision for the final system, just like that initial house plan. And the material points out that architecture isn't just one thing either. It has several key aspects, dimensions to consider.
And importantly, it's not like there's this sharp black and white line between architecture and design. This chapter really emphasizes they exist on a spectrum.
Right.
A lot of decisions aren't purely one or the other. They fall somewhere in between.
Okay, this is where it gets really interesting, I think. The material gives us some clues, some ways to figure out where a decision lands on the spectrum.
Yeah.
One big indicator is whether it's strategic or tactical.
Strategic versus tactical.
Strategic decisions, they have a long-range impact. They shape what you can do later that leans heavily towards architecture. Tactical decisions are more immediate, more self-contained. That's more like design.
That makes sense. And another clue is the effort involved, right?
Yeah, exactly.
If it's a huge amount of work to change your mind later, like fundamentally changing how the system is put together, switching architectural style.
Oh, yeah, big rewrite stuff.
That's definitely architecture territory. But if it's a relatively quick tweak, like rearranging some fields on a UI,
Simple stuff.
that's clearly design.
And the last clue they mention is trade-offs. If a decision forces you into making significant trade-offs, where choosing option A means you really sacrifice something important you could have had with option B, that's a strong signal. It's an architectural concern.
Yeah.
The chapter really drives home that most decisions aren't purely black or white. So, the takeaway. Think long-term impact, big effort, major trade-offs. Probably architecture. Quick fixes, fine-tuning, probably design. Keep that yardstick handy.
Okay, so moving on from that distinction, the next big question is, beyond just what the software does, the domain, the business problem it solves, what other critical things do architects have to consider for a system to actually be successful? How do we define these non-functional requirements, essentially?
Right, because it's not just about features. This leads us straight into the idea of architectural characteristics. The material describes these as the essential operational capabilities, the internal structural choices, and other necessary qualities of a software system, regardless of the specific problem domain.
What's fascinating here, I think, is that these aren't usually about what the software does, but how it does it.
Exactly, how.
And maybe even why certain choices were made. Things like, performance goals or scalability, how it handles more users, or reliability. These are crucial architectural characteristics that might not even show up explicitly in the initial requirements list.
Yeah, they're often implicit, aren't they? And the sheer number of potential characteristics can be, well, a bit overwhelming. The chapter wisely warns against trying to boil the ocean, trying to account for every single possible exality.
Right, you never get started.
It's about focusing on the handful that are absolutely critical for this application to succeed.
And to help make sense of them, the material groups them into a few useful categories. First, there are process characteristics. These are about how the software is actually developed and maintained.
Like agility, testability.
Yeah, things like agility, modularity helps here too, testability, deployability. How easy is it to get changes out?
Okay. Then there are structural characteristics.
Right. These describe the internal qualities of the system itself. Think maintainability, security, a big one, extensibility. How easy is it to add features later?
Makes sense. Operational characteristics. That sounds like runtime stuff.
Exactly. How the system behaves when it's actually running. So scalability, performance, availability as of when you need it, elasticity, fault tolerance, recoverability, all that good stuff.
And finally, cross-cutting ones.
Yeah, these tend to touch many parts of the system. Security pops up again here often. Authentication, authorization, usability, accessibility, maybe compliance or privacy concerns.
It's also interesting that many of these characteristics aren't simple things, like performance.
Right. It's composite. Performance isn't just, raw speed for one request. It could be latency, throughput, concurrency, consistency of speed under load.
Lots of facets. So where do these characteristics actually come from? How do we identify them?
Well, the chapter suggests a few sources. They can come directly from the problem domain, like a requirement to support 1 million concurrent users clearly translates into a need for scalability and concurrency.
Okay, from the requirement.
It can also come from the environment's sort of organizational priorities.
Right.
Maybe the company has a massive focus on security, or perhaps time to market is paramount, pushing agility.
Right, the context matters.
And sometimes they're just implicit needs. You probably always want a system to be reasonably maintainable, even if no one explicitly wrote it down.
True. You don't want to build something impossible to change later.
Exactly. The material emphasizes you need to balance the core business goals with these architectural characteristics. It even offers a guideline, the magical number 7, suggesting you should try to focus on maybe around 7 crucial characteristics to keep things manageable.
Just the most important ones.
Yeah, the ones that really drive the big decisions. They call these the driving characteristics. Those are the ones that will have the biggest impact on your architecture.
Okay, driving characteristics. Got it. So we know what architecture is versus design. We know about these important characteristics. But how do architects actually make the choices, especially when there's so many options?
Well, that leads us perfectly into our next area, which tackles the, let's say, fundamental reality of architectural decisions. There's rarely a single perfect solution.
Right. Which brings us to the 2 laws of software architecture. The first one is pretty blunt, isn't it?
It is. It basically says everything in software architecture is a trade-off.
No free lunch.
Exactly. The material puts it strongly. If you think you've found a decision with absolutely no downsides, you probably just haven't looked hard enough yet.
Huh. Yeah, that really hits home. Every path you choose, architectural path, means giving something else up. The chapter illustrates this with a nice example of deciding between, say, message queues versus topics for communication between system parts.
Right. Queues give you certain guarantees, like one message goes to one processor.
Point-to-point reliability.
But they can create tighter coupling sometimes. Topics, on the other hand, are more flexible, publish, subscribe, multiple listeners. But you might lose that guarantee of exactly once processing for a specific listener easily. Trade-offs.
This constant give and take is why the chapter really stresses the importance of trade-off analysis. It's not just picking something, it's a deliberate process.
A collaborative process, usually. You dig into the pros, the cons of each potential option before you commit. You have to weigh those architectural characteristics we just talked about. What do you gain in performance, but maybe lose in maintainability? Or vice versa.
And this ties right back to that communication example again. The material looks at asynchronous communication, like messaging,
Queues, topic.
versus synchronous communication, like direct REST calls. Async can make your system feel more responsive, maybe handle failures more gracefully in some ways.
Yeah, more resilient sometimes.
But it can add complexity, right? Managing conversations, ensuring data consistency across steps can be harder. Synchronous calls are often simpler for straightforward request response, but they can cause bottlenecks or create tighter dependencies. Performance hits, maybe?
It's always a balance. And to keep track of these crucial decisions and why they were made, the chapter introduces something really valuable. Architectural decision records. or ADRs.
ADRs.
Think of them as like little documents. They capture the architectural choices you make, the context around them, the actual decision, and crucially, the consequences, both good and bad.
And this leads straight into the second law of software architecture.
Which is?
Why is more important than how.
Ah, yes. Critically important.
The chapter emphasizes that just stating what you decided isn't enough. You absolutely need to record why you made that choice. That rationale is pure gold later on.
Totally. Especially when the team changes, or months down the line, you need to revisit why on earth you chose option X instead of Y.
So what does a good ADR look like then?
The material breaks it down nicely. It starts with a clear title, often with a number for tracking. Then the status is proposed, accepted, maybe superseded by a later decision.
Okay, basic admin.
Then the really important parts. Context. What was the situation? What forces were pushing this decision? The decision itself. Clearly state what was chosen.
The consequences.
Yep. Both the positive outcomes you expect and the negative ones, the trade-offs you accepted. You need to be honest about those. Then maybe governance. How will this be enforced? And finally, a section for notes, any extra bits of info.
So these ADRs become the project's memory, essentially.
Exactly. They track the evolution of the architecture and the reasoning behind those key turning points. Super valuable.
Okay, so we've got the architecture versus design distinction, the vital role of characteristics, the reality of trade-offs and documenting them. Now, how do we actually start putting the pieces together? How do we start structuring a system?
Right. Now we're getting into the building blocks. This next area focuses on logical components. This chapter is all about how you identify and create these functional units that describe how the different parts of a system fit and work together.
Logical components. So not necessarily physical servers, but the functional pieces.
Precisely. The material stresses that a logical component should have a really well-defined role and a specific set of responsibilities. Think of it like a distinct modular package in your code base, often represented by, say, a directory structure.
Okay. And how do we figure out what these components should be?
The chapter outlines a sort of continuous four-step process. First, you identify an initial set of components. Second, you assign the system's requirements to these components. Third, you analyze each component's responsibilities, make sure it's not doing too much, that it's focused. And fourth, you analyze how these components impact those architectural characteristics we talked about earlier, performance, maintainability, etc.
And how do we do step one, identifying the initial components?
The material suggests a couple of main approaches. One is the workflow approach. You map out a primary user journey, like booking a flight or ordering a product.
User steps.
And assign the different steps in that workflow to different components. So maybe a search flights component, a select seat component, a payment component.
Makes sense. What's the other approach?
The actor-action approach. Here, you identify the different actors, users, other systems that interact with your software. Then you assign the actions they perform to specific components. For example, a customer actor might perform place order or view history actions, mapping to order management, and account history components.
Ah, okay. Actor action. Now, there's a warning here, isn't there, about the entity trap?
Yes, a really important one. This is where you fall into the trap of creating components directly based on your main data entities, like a customer component or an order component.
Why is that bad? Seems logical at first glance.
It can lead to these massive, really ambiguous components that end up having way too many responsibilities lumped together. It makes the whole architecture messy and hard to manage. The chapter even warns about names ending in manager or supervisor, or even just service. Sometimes they can be code smells for this trap.
Okay, avoid the giant God components. Got it. So once you have your components identified, you assign requirements to them based on their roles.
Right. Make sure everything the system needs to do has a home.
And this naturally brings up coupling, doesn't it? How much these components depend on each other.
Exactly. The chapter talks about afferent coupling, that's incoming dependencies, when other components rely on your component, and efferent coupling, that's outgoing dependencies, when your component relies on others.
And high coupling is generally bad news.
Usually, yes. It can cause headaches. Makes the system harder to change, harder to test, harder to maintain, because a change in one place can ripple out and break things unexpectedly elsewhere. The law of Demeter gets a mention here.
Talk only to your immediate friends.
Basically, yeah. A component should have limited knowledge of other components, just its direct collaborators. It helps reduce that ripple effect.
But there's a trade-off there too, right?
Always a trade-off. The chapter points out that while loose coupling is generally good, if you take it too far, you might spread the understanding of a business workflow across too many tiny components. that can actually make it harder to see the big picture of how something gets done end to end.
Interesting balance. So you can sort of measure the total coupling by looking at all the incoming and outgoing arrows for each component.
Yeah, it gives you a sense of the overall interconnectedness or potential complexity.
Okay, so we've broken the system down into logical parts. Now let's talk about organizing those parts into bigger patterns. Our next topic is a really common one.
A very common one indeed. We're diving into layered architecture now. This is probably one of the most well-known approaches. It organizes an application into distinct layers based on technical concerns. The chapter uses that classic peeling an onion analogy.
Right. So what are the typical layers?
Usually, you've got a presentation layer that's the UI, what the user sees and interacts with. Then a business rules or workflow layer. This is where the core application logic lives. And finally, a persistence layer, which handles all the data access, talking to the database.
Presentation, business, persistence. Got it. And it's popular because...
Well, a big reason is it's relatively easier to understand and get started with. It also maps pretty cleanly onto familiar design patterns like Model View Controller MVC.
Ah, okay. How does that mapping work?
Often, the view part of MVC sits in the presentation layer. The model relates closely to the persistence layer, handling data, and the controller orchestrates things, often residing in that middle business workflow layer.
Makes sense. And the chapter mentions how these logical layers translate to physical deployment, right? Like 2-tier, 3-tier.
Exactly. You could have a simple 2-tier where the client application talks directly to the database, or a more common 3-tier with a dedicated application server sitting between the client and the database. You can even have more distributed setups. And each of these physical arrangements has its own trade-offs, simplicity versus scalability versus reliability.
So why choose layered? What are the drivers?
The material highlights a few key reasons. Ease of understanding is a big one. That mapping to common patterns like MVC. Just how common it is generally makes it quicker for teams to adopt. And sometimes it aligns well with how organizations structure their teams based on technical skills. UI team, back-end team, database team.
Okay. And its strengths, its superpowers.
Well, feasibility is one. Its relative simplicity can make it quick to get a project off the ground. For well-designed monoliths, single deployment units where layers don't involve network calls between them, performance can actually be quite good.
Right. No network latency between layers.
Maintainability is generally seen as a strength due to the separation of concerns. UI code is separate from business logic. And testability teams often have established ways to test each layer.
But it's not perfect. What's the kryptonite? The weaknesses.
It can get complex and unwieldy as the application gets really big, the so-called monolith problem. Reliability can be just medium, especially in physical deployments where network dependencies between tiers can cause issues. And scalability and elasticity often aren't as good as more distributed architectures.
And there was something about the business logic.
Yeah, a key criticism is that the problem domain, the actual business functionality, can get smeared across multiple technical layers. A change to a business rule might mean you have to modify code in the presentation layer, the business layer, and the persistence layer.
Ah, okay. Changes ripple vertically through the tech stack.
Exactly. The chapter also mentions you can add other layers, like a services layer for external integrations, but the core idea is separating by technical function.
Right. Okay, so layered architecture separates by technical concerns. What if we want to organize things differently, maybe more around the business itself?
Ah, that leads us perfectly into our next architectural style, the modular monolith. This approach divides the application based on business capabilities or domains rather than technical layers. But, and this is key, it's still deployed as a single unit, a monolith.
Okay, so still one deployment, but internally organized differently. How does that work?
Instead of presentation business persistence layers cutting across the whole application, you partition the application into distinct modules, each representing a specific business area. Think orders, customers, inventory, shipping.
Business domains as the top-level organizers.
Exactly. Now, inside one of these modules, like the orders module, you might still internally use layers, maybe some UI components specific to orders, business logic for order processing, data access for order data. But the primary architectural partitioning, the main way the application is divided, is at that domain level.
And the goal is?
The main goal is to create loosely coupled modules. You want changes within the inventory module, for example, to ideally have little or no impact on the orders or customers modules.
So it tackles that domain smearing problem we saw in layered architectures.
Precisely. If a business rule about placing orders changes, you ideally only need to modify code within the orders module, not across multiple technical layers that span the entire application.
How does this look in the actual code?
It can vary. Modules might be represented by different namespaces or maybe separate project folders within the same source code repository. Crucially, each module needs a clear, well-defined public API or interface that dictates how other modules can interact with it. You need to enforce these boundaries.
Can you enforce them technically?
Yeah, the chapter mentions things like the Java Platform Module System, JPMS, or using .NET namespaces with internal keywords to hide implementation details. You can also use architectural fitness functions or static analysis tools to help maintain these module boundaries over time.
What about the database? If it's all one deployment, is it still one big database?
Whoa, that's a tricky point. You can extend the modularity to the database, maybe by having separate tables or even database schemas for each module's data. But you have to be really careful. The chapter warns against allowing direct SQL joins between tables belonging to different modules.
Because that just reintroduces tight coupling at the database level, right?
Exactly. You undermine the whole point of the modularity if modules are secretly tied together through the database.
So what are the big advantages, the superpowers of this modular monolith approach?
Better alignment with business domain changes is a huge one. It generally leads to improved maintainability and testability within each module. And it can enable cross-functional teams, each focused on a specific business domain, to work more independently, potentially speeding up development.
Sounds pretty good. What's the trade-off?
The main trade-off is that achieving and maintaining this modularity requires more upfront thought, ongoing discipline from the team, and potentially more sophisticated tooling compared to a simple layered approach. It's not automatic. You have to actively work at keeping those boundaries clean.
Makes sense. Discipline is key. Okay. One more major style to cover today, one focused on flexibility and customization.
That's right. Our final stop for this deep dive is the microkernel architecture. This style is really interesting. It consists of a minimal core system providing only the absolute essential functionality, plus numerous independent plugins that add specific features or variations.
Core and plugins, like a browser with extensions.
That's a pretty good analogy, yeah. It's particularly suited for applications that need a high degree of customization or extensibility, where you want to easily add or swap out functionalities.
So the core stays small and stable?
Ideally, yes. The core system contains only the essential, stable functions that rarely change. All the optional features, the variable parts, the custom bits, those are all implemented as separate plugins.
And these plugins are independent?
Generally, yes. They're often developed and can even be deployed independently. They communicate with the core system, usually through some well-defined interface or contract. Direct communication between plugins is often discouraged.
Why is that?
To keep things decoupled. If plugins need to interact, the core often acts as an intermediary or provides some kind of registry or event bus for them to communicate indirectly. Keeps the core in control and avoids complex inter-plugin dependencies.
How is this typically deployed? Is it a monolith or distributed?
It can be both. Often, microkernel architectures are deployed monolithically. The core and all its currently active plugins are packaged and run as a single unit. But the chapter also mentions distributed microkernels are possible, where plugins might be deployed as separate services.
Okay. And communication between core and plugins, sync or async?
Again, depends on the need. It could be synchronous calls for immediate results or asynchronous messaging if plugins handle background tasks or don't need to block the core.
The chapter mentions microkernality. What's that?
Yeah, it's a measure of how functional and stable the core system is without any plugins attached. A truly microkernel has very minimal functionality on its own, but provides the essential hooks and stability for the plugins to do their work.
Right. So superpowers, extensibility seems obvious.
Absolutely. Excellent extensibility and customizability are the key strengths. Need a new feature, build a new plugin. Want to offer different versions of a feature, implement them as separate plugins. You can add functionality without touching the core code, which is great for stability.
And the trade-offs. For the monolithic version first.
For monolithic microkernels, the main challenge can be managing all the plugins, versioning, dependencies, deployment complexity, even though it's all in one unit.
And for the distributed version?
For distributed microkernels, you get better scalability perhaps, maybe more technology choice for different plugins, but you inherit all the usual challenges of distributed systems. Network latency between core and plugins, increased operational complexity, managing distributed transactions if needed. Performance can definitely be a trade-off due to those network calls.
So where would you typically use this style?
The chapter suggests it's well-suited for things like IDEs or developer tools with extension marketplaces, integration hubs connecting diverse systems, platforms designed for A/B testing different features. Each feature variant could be a plugin, or any system where customization and evolving features are paramount.
Makes a lot of sense. Okay. Quite a journey through different architectural ideas.
Definitely. So just to wrap things up and recap the key points from our deep dive today.
Yeah, let's pull it together. We started by getting clear on that crucial difference between software architecture, the big structural decisions, and software design, the implementation details within that structure.
Then we looked at architectural characteristics, those vital non-functional requirements like performance, scalability, maintainability. We saw how they're categorized, where they come from, and the importance of prioritizing the critical few, the driving characteristics.
Then came the laws. First law, everything is a trade-off. No magic bullets. We saw the need for careful trade-off analysis.
And the second law, why is more important than how, which led us to architectural decision records, ADRs, as a way to capture not just the what, but the crucial why behind our choices.
Then we moved into building blocks, logical components, how to identify them using workflows or actors' actions, avoiding that entity trap, and understanding coupling both afferent and efferent.
We then explored specific styles. First, the common layered architecture, organizing by technical concerns, presentation, business, persistence, noting its understandability, but also potential issues with domain smearing and scaling.
Followed by the modular monolith, organizing by business domain within a single deployment. Better alignment with business changes, better module independence, but requires discipline to maintain those boundaries.
And finally, the microkernel architecture, with its small core and independent plugins, offering fantastic extensibility and customization, but with its own trade-offs depending on whether it's deployed monolithically or distributed.
It's really clear from all this that understanding software architecture isn't just nice to have. It's a truly vital skill for anyone involved in building software. Grasping these core concepts gives you a solid foundation.
Absolutely. And maybe the biggest takeaway is that there's rarely a single right architecture. The best approach is always context-dependent. It depends entirely on the specific problem you're solving, the specific requirements, those architectural characteristics you prioritize, and crucially, the trade-offs you're willing to make.
So we really encourage you, the listener, to think about how these concepts, layers, modules, kernels, characteristics, trade-offs relate to projects you've worked on or systems you use. Which styles might have been a good fit or maybe a poor fit, and why?
And maybe a final thought to leave you with. Learning architecture is definitely a continuous journey. It's not something you master overnight. But developing that ability to analyze problems, to clearly see the trade-offs, and to choose the right building blocks for the job, that's absolutely essential for creating software that's not just functional, but truly resilient, adaptable, and successful in the long run.